Okay, so this is the second half of section 7.3. The first half was the addition principle, which went along with Venn diagrams. And here we have the multiplication principle, which goes along with something called a tree diagram. So what we'll do is an example, if I can write correctly, x amp O, and an example that leads into the definition of the multiplication principle. And then some more examples covering some problems in section 7.3. So 14 through 20 and 35 and 36. And then some other examples covering 53 and 54. Okay, and that would bring us to the end of 7.3. We'll see the multiplication principle in a number of different places, especially when we get into chapter 8. So, what is the multiplication principle? Well, the basic, most original, not most original, but the basic example is, for multiplication principle, is flipping a coin. So, a quarter or something with heads and tails. If you flip a coin twice, how many outcomes are possible? And when I say outcomes, I'm not saying counting the number of heads and tails, right? We just want to record what happens after each time you flip it. So if you flip a coin twice, on the first flip, you can get heads or tails. So there's two outcomes. On the second flip, well, if you flipped it heads on the first, you get heads or tails on the second. Or if you got tails on the first one, you could get heads or tails on the second. Right? So there's actually 4 outcomes here. You could get head and then head, head and then tail, tail and then head, tail and then tail. Those are the 4 possible outcomes of flipping a coin twice. Okay. So there's a couple of different ways to count this 4 outcomes. I mean, 4 outcomes is pretty easy to count because there's only 4, but one is to take this and think of it as being a sequence of things, a tree diagram that looks like this. So a tree diagram takes a sequence of actions and just runs through the possibility. First flip, you can get heads or tails. So this is my first flip. After you got a head and you flip it again, you can get heads again or tails. After the first flip, if you got tails, you flipped again, you could get heads or tails. And so this is the sequence: first heads and then heads again, first heads and then tail, tail and then head, tail and then tail. So that counts all 4 of us. So this entire branch is one outcome of flipping a coin twice: get a head and then another head, head and then a tail, tail and then a head, tail and a tail. How many options were there? There's 2 outcomes for the first flip. And then the second flip, 2 outcomes there. You could get heads or tails. Once you've done the first flip, the second flip gives you 2 outcomes. So 2 times 2, 4 outcomes total. Right? And so that's the other way to think about counting the number of outcomes that you get from a sequence of actions. 2 choices on the first flip, 2 choices on the second flip, 4 choices total, 4 possible outcomes. And this is the multiplication principle. For a sequence of actions, right? So here's flip the coin once, record what it is, flip it again, record what you get. The number of possible outcomes is the product of choices at each step. So for this coin flipping problem, you have 2 choices at the first flip, you could get a heads or tail, and 2 choices for the second flip, you can get a heads or tail. So how many possible outcomes are there? There's 4. Heads, 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 tails, tails, heads, tails, tails. So flip a coin 3 times. So another example. How many outcomes? Well, you could count them. You could get a head on the first flip, and then a head on the second, and a head on the third. Or you could get a head on the first, and a head on the second, and a tail. Or you could get a head and a tail, and then a head, or a head and a tail, and then a tail. Or you could get a head, oops. You could have a tail, and then a head, and a head, and a tail, and a head and a tail, or you could get a tail and then a tail and then a head, or a tail and a tail and a tail. So 8 possible outcomes. You can see how this would get really tedious if you had to do, flip a coin 20 times, how many outcomes. So the multiplication principle says, well, just look at how many outcomes you have at each step. How many outcomes are there if you flip the coin the first time? 2. If you just look at the second flip, how many possible outcomes are there from just the second flip alone? Well, the second flip will give you heads or tails, so that's 2. How about the third flip? Well, that'll also give you 2. So 8 total. There's my multiplication principle in action. 2 choices the first time, 2 choices the second time, 2 choices the third time, so 8 possible outcomes. 2 times 2 times 2. You can also do this as a tree diagram, but it gets a little tedious having to draw 8 of these things. All right. Head on the first flip, head on the second flip, head on the third flip. That's the head, head, head option. Head, head, tail, head, tail, head, head, tail, tail, and same for these 4 and these 4. Right? So an outcome here is what is the sequence of heads and tails you get if you flip it 3 times. How many outcomes are there? Well, 8. And so that's what the multiplication principle is. You multiply the number of steps at each, the number of outcomes at each step. So, example. So problems, well, most of the problems are like this. So 14 through 20, and I guess that's 35 through 39. Dealing with, well, one of the examples they use are code words. So you and your friends have set up a secret code, right? And you say, well, we'll only use the first 6 letters, and we will create words of 3 letters each. So how many 3-letter code words can be made from the first 6 letters? Right. And of course, many of you use code words all the time, like OMG or BFF, those sort of things, right? So what we're talking about here is things like, you know, AAA, that might stand for something, or ABC, that might stand for something else, or AFB, maybe that stands for something. But how many different ways are there to arrange 3 letters from the first 6? Well, it's a sequence. So we use the multiplication principle. We pick the first letter, and then we pick the second letter, and then we pick the third letter. How many choices do you have? Well, we're only doing 6 letters, so 6. Once you've made the first choice, how many choices do you have for the second one? Well, we'll still have the same 6 letters, so that's 6. And if we're choosing the third letter, how many letters do we have to choose from? We still have 6. So that must be 6 times 6 times 6, 216 possible code words. Right. And you can do variations on this. How many code words are there? You know, same setup, 6 letters, 3 letters in each code word, that don't use the same letter twice. Well, again, it's a multiplication principle, because we're going to choose the first letter and then the second letter and then the third letter, so a sequence of choices. How many choices do we have for the first letter? Well, since we haven't used any of them, we can use all 6. For the second letter, though, we can't choose whatever the first letter was, so there's only 5 choices for the second letter. And so for the third letter, well, we can't use whatever letter we use for the first one. We can't use whichever letter we use for the second one. So now we have only 4 options. 5 times 4 is 20, times another 6. It's 120 possible code words that don't use the same letter twice. So how many code words are there that use the same letter at least twice? Well, 94, right? Because 120 don't use it at all. Use the letter at least twice. Well, there's 216 total. 120 don't use the letter twice. So, what's the 94 that's left? Those are the 94 code words that use the letter twice. So that's a nice way to think about it. So note that this is not actually a multiplication principle problem, but you know, once you have these 2, you can figure out how many code words use the letter at least twice. So it's a sequence of choices. Whenever you have a sequence of choices, you multiply the number of choices at each step to get the total. So a similar problem, a buffet offers 7 types of appetizers, 3 types of entree, and 10 types of dessert. You're allowed to pick one of each. So, how many choices for dinner do you have? Right. So you go through the buffet and you can pick one of these 7 things, one of these 3 things, and then one of these 10 things. Well, appetizers, you got to choose one of 7. You've got 7 options for that. Entree, your main meal, there's 3 options for that. And you can pick one of the 10 desserts. So 210 possibilities on your one plate. Okay, so a sequence of choices, multiply the number of sequence of choices together to get the possibilities. Okay. And word problems. This is like problems 53 and 54. So suppose the business college has a student council. We'll just say a student group. And the student group has 8 accounting majors, 14 real estate majors, and 7 finance majors. A 3-person committee is being formed with 1 person from each major. How many possible such committees are there? Well, same deal, right? First person, well, you have to pick 1 accounting person, an accounting representative, and they have to pick a real estate representative, and then you have to pick a finance representative. How many choices do you have for accounting? 8. How many for real estate? 14. How many for finance? 7. And that should be, I think 784 is what my notes say. So 784 possible committees if you have to have 1 from accounting and 1 from real estate and 1 from finance. Suppose you want a 3-person committee now. Formed without restrictions about who's on it. Right? So you're not saying there has to be an accounting major and a finance major, it's just 3 people. Well, how many choices do you have? You have to pick the first person, then you have to pick the second person, then you have to pick the third person. How many people do we have total? 8 plus 7 is 15, 29 people to choose from. The first choice, well, there's 29 of them. Second choice, well, you've already picked 1 person, so now there's only 28 possibilities. And the third choice, well, now there's 27. So 29 times 28 times 27 is the number of possible committees that can be made without worrying about who's on what major. And this should be 21,924 possible 3-person committees. And what we'll find out in section 7.4 is that that's something called a permutation. And we'll see that again. So, multiplication principle is pretty straightforward, at least compared to the addition principle. Multiplication principle is the number of possible outcomes for a sequence of actions. The number of possible outcomes is the product of the choices at each step in the sequence. So you figure out how many choices you have at each step, multiply